We will now define the connection polynomial for an LFSR. So we have seen the general form of an LFSR, which is given as follows, where we compute the new symbol that we input to our shift register or to our LFSR as a linear combination of the symbols that we have already inside our LFSR. And exactly how this is computed is determined by the constants here that we call C1 up to CL. So our LFSR is completely determined by the vector here that we call C, which is first a 1, and the 1 here will correspond to that we have C0 here equals to 1. So we can call this one C0. And then we have all the other constants here, C1 up to CL. So this vector here will completely determine the feedback for our LFSR. And the D transform of this C here is given by C of D, which equals 1 plus the sum where I goes from 1 to L of Ci times D to the I. And this polynomial C of D is called the connection polynomial of our LFSR. And since this 1 that we have here comes from the fact that C0 here equals 1, it means that we can write this as a sum where I goes from 0 to L instead of 1 to L, and then we have Ci times D to the I. So let us look at an example here of a connection polynomial. So we have our feedback to the shift register here, which says that C0 equals 1, and this will always be the case if we have a feedback. Then we have here that C1 will be equal to 1. We have that C2 is equal to 1. We have C3 equals to 1. And here we have C4 equals to 1. So our connection polynomial for this LFSR, C of D, is written as 1 plus 1 times D, because this is C1 times D, plus D squared, because it is C2 times D squared, and then we have C3 times D cubed, so we have D cubed, and then we have C4 times D to the 4, so we have D to the 4 here. So the connection polynomial for this LFSR is given by 1 plus D squared plus D cubed plus D to the 4. So here is another example of an LFSR which has another connection polynomial. So what is the connection polynomial of this one? Well, we have C0 equals 1, C1 equals 1, we have C2 equals 0 because there is no feedback here, we have C3 equals 0 because also here there is no feedback, and then we have C4 equals 1. This means that our connection polynomial is 1 plus D, and this D comes from the fact that C1 equals 1, and then we have plus D to the 4 because C4 equals 1. So here we have the connection polynomial for this shift register. A shift register also gives rise to a recursion, and the shift register recursion can be written as a sum where I goes from 0 to L of Ci times Sj minus I, and this equals to 0 for all j is larger than or equal to L. And in this case we have said that C0 equals to 1. And we can prove this if we look at the general form for our LFSR. So we have that for all j is larger than or equal to L, we have that Sj, this bit that is computed, is written as CL times Sj minus L plus CL minus 1 times Sj minus L plus 1 plus, and then we continue all the way to C1 times Sj minus 1. And this here we can write as the sum where I goes from 1 to L Ci Sj minus I. So if Sj equals this sum here, we can also write this as Sj plus this sum here, where I goes from 1 to L, Ci Sj minus I, this equals to 0. And if we now say that C0 is equal to 1, then we can say that C0 Sj plus the sum that we have here for I goes from 1 to L, Ci Sj minus I, this equals to 0, which will give us that we can go from I equals 0 to L instead, where we have Ci Sj minus I, and this will equal to 0. So this shift register recursion that we have here follows directly from how we defined our shift register and how we wrote our shift register in this general form that we have here.